Thank you for joining today's webinar organised by Anatune Limited and SIFT Technologies. I'm Vaughan Langford, a Principal Scientist at SIFT Technologies, the world's leading supplier of direct mass spectrometry for volatiles analysis. I started with SIFT Technologies on the founding of the company in late 2002 and have been an application scientist here ever since. My current role with SIFT Technologies focuses on SIFT-MS education, training and advanced customer support. For the past 4.5 years, I've had the privilege of collaborating closely with Dr Mark Perkins, Senior Applications Chemist at Anatune Limited. I'm delighted to introduce Mark to you today. Mark joined Anatune in early 2015. His current role supports and expands the analytical capability of SIFT-MS, with a particular focus on autosampler integration and the development of automated test methods. Prior to joining Anatune, Mark graduated from the University of Southampton, United Kingdom, with a PhD in electrochemistry. He then joined the Malaysian Rubber Boards United Kingdom Research Centre as a senior analyst, running the gas and liquid chromatography section, eventually becoming the head of the whole analytical section. Mark is based at the headquarters of Anatune Limited in Cambridge, UK. Anatune is the UK's leading supplier of automated analysis solutions. After Mark's presentation, we'll conclude with a live question and answer session, so please add your questions through the GoToWebinar portal. And now it's my pleasure to hand over to Mark to describe how SIFT-MS methods can be validated. Thank you very much, Mark.
Thank you, Vaughan, for that introduction. And as Vaughan's mentioned, today's webinar is looking at method validation on SIFT-MS. So some of the previous stuff we've talked about in previous webinars has been looking at developing methods to do analysis on samples, very much as we would for other chromatography techniques. And one of the most important things you can do when you've developed a method is to validate it. And questions about how to validate SIFT-MS methods have been around for a while. Is it possible to do it? And what I hope to show you today in this webinar is it's entirely possible to validate SIFT-MS methods to make them robust, usable, analytical methodology. The first thing to discuss, I think, is going to be what's the difference between a SIFT-MS and a GC method in terms of the development, so that we can then understand how to validate the method. So here on this slide is just a quick summary of the similarities and differences. So the GC method, for example, you have to pick a column, you have to understand your sample introduction, you have temperature programs in the oven that you need to play with to sort out your chromatography, and you have a choice of detectors. Now with SIFT-MS, we don't have a column in the system. There's no chromatography. We have direct introduction of the sample into the system. So we actually remove some of the complexity of our method development and consequently our validation by removing the column from the system. We also don't get a choice of detector. It is a mass spec detector. That's how it works. So again, we don't have any added complications about ways to look for the sample as it comes out the back end of the column. So what we're left with really are those two bits in the middle, the sample introduction and how we actually separate the samples out. So for a GC-MS method, that is introducing the sample through an injectable inlet, and then we use an oven program to separate the compounds on the column. SIFT-MS, we introduce the samples very much in the same way through an injectable inlet for automated methods, or maybe by hand if we're doing a non-automated method or a more gas phase type analysis. And then we use reagent product line pairs to sort of do our separation. So an analogous separative technique in a way. Now the thing to say about GC-MS method development and consequently validation is that once you have the samples in the system, you have to allow the method to run to completion. So they're on the column and there is a finite runtime on the column. You have to get the compounds from the front end to the back end, and these run times are the order of 20+ minutes in some instances. And so if you make a mistake or you have a problem or your methodology isn't perfect, what you're actually having to deal with is waiting for 20+ minutes for the system to reset itself back to its starting state for you to make a change and then rerun the sample and reanalyze the data coming out of the back end. For SIFT-MS methods, there is no column, as we've discussed already, and the sample clears itself through the flow tube in a matter of milliseconds, such that the system will actually reset itself very, very quickly back to its starting point. And you can stop the method at any time, allow the system to reset, and then start again. And all you're really waiting for is the automated system to catch up with itself to add the sample back into the system. So our run times are very often less than a minute. So you can see if we have to make changes to our method or vary some of the parameters for our validation exercises, it's much, much more swift than it would be for a GC-MS method. And this does have consequences in the way that we do validations and the way we run methods. So what I'm going to do with this webinar is we're going to look at two different validations. One's going to be sort of manually introduced gas phase analysis, looking at formaldehyde, and then we're going to follow that by a much more complex automated sample prep type method that looks for BTEX compounds in soils. So let's first have a look at the formaldehyde validation. Point I want to make at this stage is that all of the work done for this validation was carried out by Joe Wicks at Intertech Pharmaceutical Testing Services at Manchester. So this is all his data. He carried it out for a customer of theirs to validate a method for a pharmaceutical product for regulatory release. So I'm thankful for Joe to allowing us to present this data. So just to walk through his presentation, the first thing to discuss is, are there opportunities for these direct mass spec techniques in analysis for pharmaceutical products? Well, there is, and volatile compounds can be harmful to the patient, and in many instances we're looking at VOCs coming off of packaging materials or just drug delivery devices such as aspirin inhalers, for example. And if we don't control these or analyze for these, there can be significant costs in product recall. And what we found is SIFT-MS can determine these volatiles really, really quickly in packaging materials, headspace of pharmaceuticals, drug delivery systems. So this is a perfect technique for this type of analysis. These direct mass spec techniques, particularly SIFT-MS, are perfect for this sort of analysis. So what sort of analytes can we look at for these types of methods? Well, there's the residual solvents such as those listed in the ICH guidelines and USP 467. Polar organic materials, for example, formaldehyde, which, as many of you may know, is a very difficult compound to analyze and is actually present in lots of packaging materials, and thus is something we need to look at. Also, other VOCs that are difficult to analyze, such as the other aldehydes or ketones or esters. There may be a need to look at volatile inorganics depending on pharmaceutical product, hydrogen sulfide, hydrogen cyanide, ammonia. I mean, there's other issues at this point in time looking at the volatile nitrosamines in drug materials, which is currently a bit of a vogue issue. So there are needs for these sort of volatile type analyses with pharmaceutical products. And the last but not least, volatile leachables from packaging. So of course this leads us to the applications that a pharmaceutical analysis would be. So we're looking at residual solvents as discussed, packaging stability, taint analysis, continuous monitoring of release from formulation product over time. Maybe we are looking to produce tablets or compound these things up with excipients, and there may be some heat generated which may lead to degradation. Can we follow these dynamic processes over time? Absolutely. With SIFT-MS, the sensitivity and the continuous monitoring allow us to do this. So it's a perfect analysis technique for pharmaceutical applications. It's all going to be gas phase, this analysis. SIFT-MS is a gas phase VOC analyzer. So all the analyses are carried out in the gas phase, and so all concentrations are quoted as ppm or ppb by volume. Now we can convert this by using the various parameters and equations as listed on this slide, but basically gas phase analyses, so it's going to be the ideal gas equation comes into it somewhere, but I'll leave that for you to work out. So let's look at the requirements of a method validation for SIFT-MS. So this analysis was basically looking at a drug delivery device that had polymer materials in it, and these polymer materials released formaldehyde into an enclosed packaged space. So these are pouched devices, and they were interested in looking at the formaldehyde concentration in the packaging within the pouch itself. And so we needed a method that would find formaldehyde, and B, then validate that method to the requirements of a regulatory submission. So, as we said, the formaldehyde was in the headspace. We're going to treat it as an impurity as it is coming from the underlying product delivery system. And so we can follow a number of different validation techniques. There's the ICH Q2 guidelines, which are based on pharmaceuticals. or there's some other ones based on pesticides, such as the Sanko version here. But this being a pharmaceutical product, ICH Q2 guidelines seem to be the best approach to take for this one. At the point this was done, I don't think there'd been any regulatory submissions using SIFT-MS as a technique. And also the guidelines on ICH Q2 are written with more conventional techniques in mind, such as GCMS or LCMS. So the question here was, could we adapt this methodology to use it with SIFT-MS and still get a valid validation at the end of that? So the way this was done, we worked through the ICH, I say we, Joe Wicks worked through the ICH guidelines one by one and looked at what was needed and saw if we could apply it to SIFT-MS. So the first part of the ICH guidelines is specificity. So basically specificity is there anything in your assay or impurities that will somehow get in the way of the analysis or analyte you're looking at? So conventionally, what we need to do is look at system blanks or a diluted standard or a matrix blank, or compare chromatograms to show there's no co-elution or matrix effects, look at peak shapes. Now, this isn't available to us with SIFT-MS because we don't generate chromatograms, we don't generate peaks, we don't have eluent or gases in the system. We are simply measuring the analyte as it is seen in the pouch of the product. So another way of looking at this would be to analyze system blank, or look to see if the analytes we were looking at would have any possible cross analysis from another compound that may be present in the system that is going to look like formaldehyde. And so the approach was to basically interrogate the SIFT library for all of the necessary product ion and reaction data in the library. Now, I will say at this point, of course, that no compound library is exhaustive, but the SIFT library is pretty much comprehensive for small volatile compounds. So by searching the SIFT library, we were very able to screen out any compounds that may look like formaldehyde. And formaldehyde, being a very small molecule, it's only 30 Daltons in weight, doesn't have very many things that look like it. So by looking at the SIFT library and interrogating it for any other compounds that may look like formaldehyde, we were very able to say that there was no interfering compound that could be in the system that we wouldn't detect as something else. And so we used that as our specificity measurement on the system and in the validation. So the next part of ICH is to go and look at the linearity of the system. So we're going to be looking at compounds over a certain concentration range. We want to know that the system is linear. So is there a linear relationship across the entire range of the method? So conventionally, you would prepare standards over the range that you're expecting to analyze in, run them down the system, plot the peak areas, heights versus theoretical concentrations. Now, this is a gas phase analysis looking at formaldehyde. So the question is, how do we prepare formaldehyde standards at variable concentrations in a known way to enable us to run the linearity? So the solution here was to get a gas standards generator, so a Kintec gas standards generator using permeation tubes to provide the analyte. And by altering the flow rate over the permeation tube and into the SIFT-MS, we could alter the concentration in that gas flow. And then by plotting the signals as a function of analyte concentration, we could then generate a calibration curve or a linearity curve for this system. So the nature of the concentrations from the permeation tube and the ability for the SIFT to cope with flow rates meant that we could vary the concentrations from around about 96 parts per billion by volume up to around about 35 ppm. And so this is the data generated for that linearity. You can see we've got theoretical concentration followed by the measured concentration, and then the third column here, the calculated concentration, is actually using the straight line data plot and then using that straight line equation to back calculate concentrations to see if we actually get a decent recovery on the measured concentrations. And you can see actually for the low end concentrations down in the 100 to 200 ppbv, it is massively over recovering. And the reason for this was because the top data point at 35 parts per million by volume is actually right at the top end concentration range for SIFT-MS in this setup, and it tends to have quite significant weight on the system. So although we get a good R squared of 997, you can actually see from the plot on the right hand side that the top point is actually skewing the curve up a bit, which is leading to a non-zero intercept at the bottom end of the system, which is leading to over calculation at the bottom end. This is telling us actually that although we see linearity based on R squared, the range of the method, i.e. the part of the linear range that we can actually work with, is actually smaller than what we're showing here. So a calculation was recarried out. Instead of running it up to 35 ppmv, we only went to 14.5 ppmv, and you can see here now that we get a really good R squared, 9998 for this linear plot, and we also get recoveries of between 95 and 115% for all points on that curve. Clearly this data works, this system is linear, the range works perfectly for this, and so a very big positive on the linearity of this system. So the next part of the validation is to look at precision. So how precise is your instrument? There's no point having a system that can't give you precise measurements. So we needed to check the precision of the instrument. It's a very important thing to check on a method validation. So basically ICF says that repeatability should be assessed using a minimum of 9 determinations covering the specified range, e.g. 3 concentrations of 3 replicates each, or maybe a minimum of 6 determinations, 100% of the test concentration. So again, what was decided here was because formaldehyde was being treated as an impurity, we're going to take a mixture of both approaches. So the idea was to take 6 measurements of 3 preparations at 50% of the linear range and measure them on the SIFT-MS. So these concentrations were prepared by using the permeation tubes and the permeation oven to generate a known concentration, running that gas flow into a Tedlar bag and using that Tedlar bag as a surrogate for the pouch product in this system. And here we can see the data generated. So the theoretical concentration we were looking at as measured from the permeation oven was 7.27 ppmv, and you can see the 6 repeat measurements. So for the 3 prep samples show RSDs of less than 0.5% for all of those measurements, with recoveries of greater than 99%, which for a precision measurement on a compound such as formaldehyde with no internal standards in the system is just a fantastically precise measurement. The system is fantastically precise for this type of measurement. This is, you know, you'd be hard pushed to get better data than that on any other system you're working on. So following on from the system precision, we now look at intermediate precision. So what do we mean by intermediate precision? Well, what we mean by that is how much do day-to-day changes actually affect the measurement. So what we need to do here is we need to repeat the precision exercise, but do it on a different day with a different analyst preparing the samples, because it may not be done by the same analyst all the time, using fresh diluent or mobile phases. If we've got them, fresh sample preps, use a different column. If the instrument's got a column in it, use a different instrument. Now, as we discussed at the beginning of this, we don't have a column in this system. It's not chromatography based. Therefore, we don't have any sort of mobile phase. We don't have, you know, gas in, diluent in the system. Unfortunately, however much we would like them to have 2 instruments, Intersect only had 1 instrument, so we couldn't perform it on a different day. But we definitely could perform this on different instrument. We definitely could perform this on different days and different analysts using standard preps. So we replicated the method before, generating gas standards in Tedlar bags and running them through the system. And this is the data generated for the intermediate precision off of a second user. We can see, again, we're looking at concentration of 7.2 ppmv for this. And again, we get similarly fantastically precise data. So our RSDs, less than 0.5%. And again, if you do the recovery off of this, our recovered concentrations are around about 99% of what we expected to see. And again, inherently precise instrument, day-to-day inherently precise as well. If you take the total statistics, 36 measurements altogether, RSDs of 0.3% for 36 measurements of formaldehyde measured in the gas phase with no internal standard. Again, I challenge any other methodology to hit those sorts of precise measurements. So a tick in the box for intermediate precision. Next part of the validation is the accuracy. So what we've done is we've determined the instrument is precise. So if you put the sample into the system, you get the same answer coming out every single time. So that's really good. So the next thing we want to look at is if we put a sample into the system, are we actually getting the right answer? Are we getting accurate response? Is the instrument, you know, inherently quantitative, or are the calibrations we're applying to it giving us a decent, accurate answer? So there is methodology for doing accuracy. So accuracy should be assessed on the sample spiked with known amounts of impurity. What we're trying to do here is show that there's nothing in the matrix that's going to interfere with the recovery of the analytes from the system. Now, one problem we have here is the conventional way of doing this is to spike samples with the impurity standard at 3 levels, triplicate preparation for each, and then calculate the recovery from the spike versus the unspiked samples. Now, to be able to do these recovery calculations, you've got to be able to be able to accurately spike in known concentrations into the sample to recover it. If you consider what we were doing with this methodology, these were drug delivery devices inside a closed pouch of variable volume. We didn't know the volume inside the pouch. We knew it contained formaldehyde, but we didn't know the volume of the pouch. So we couldn't actually accurately spike in a known amount of impurity into that pouch and recover it, because we didn't know the volume. We couldn't work out the concentration. The concentration is you know, volume by volume. If we don't know the starting volume, we can't work out an accurate concentration. So we were unable to spike into this system at this point in time. So we had to come up with a different way of doing this. So another way of actually showing accuracy is to sort of look at the linearity, look at the precision, and use those two together to come up with an approach to generate accuracy. And so in this instance, the precision test was repeated at 10% and 90% of the linear range. So we would now have precision at 10, 50, and 90%, and it should all give really good recoveries, and that will show that the system is actually accurate over the concentration range we're looking at. And so here is the data for those samples, those test samples. So again, we used the Kintek gas standard generator to generate the gas standards in the bags, one at 1.4 ppmv, one at 13 ppmv, and then basically did 6 repeat measurements across the range and looked at the RSDs and looked at the recoveries. And you can see that all samples recovered at least 90% of what was spiked into the bag in the first instance. So again, very good recovery for these analytes and analyses. So accuracy, very good for this system. So moving on in the ICH guidelines, we now look at robustness. So what do we mean by robustness? Well, what we want to do with robustness is we want to understand how robust the system is to small changes that you can't control day to day on the analysis. So if the temperature in your lab is slightly higher, is the methodology going to fall apart? If a heated zone on your system is slightly different compared to where it was before, is your methodology going to fall apart? If your column is a different length slightly for example, in the GCMS method, is it going to make a difference to the analysis? And so, you know, it's quite easy to see how we could vary things in gas chromatography. For example, we change the column, change the temperature program, change the flow rate. Same applies with liquid chromatography. So what can we do with SIFT-MS, bearing in mind that there isn't a lot to change with the SIFT-MS method and the SIFT-MS instrument? Really, when we looked at the only things that can affect the methodology, it would be the temperature of the sample inlet, as this would affect the flow into the system, and flow will determine concentration, and also the temperature of the flow tube where the reactions are taking place. So if you understand the way that SIFT-MS works as a technique, the reactions between the reagent ions and the analytes run at some fixed reaction rate. Being a kinetic value, if the temperature changes, your reaction rate may change slightly. The system as set up has control of these heated zones, but there is a tolerance on them, and the tolerance for these heated zones is plus or minus 3 degrees from the set point. So the precision exercise was repeated again at a concentration of 7.27 ppmv, with the flow tube and the inlet varied between plus or minus 7 degrees from its set point, and then looking at the recovery of those analytes in the system. And as you can see from the data presented, all recoveries were greater than 90%. So again, for the things that can change in the system day to day that you have no control over, there is no material effect on the analysis and the results being generated by the system. So again, a robust method. The next part to talk about is LODs and LOQs. Now this is essentially looking at how low we can detect our analytes in the methodology. Normally we would take a signal to noise approach, so you would standard GC methods, inject a known low concentration of analyte, or run some blank samples and look at the noise, and typically a signal to noise ratio of 10:1 would be applied to a quantitation limit, or 3:1 for a detection limit. With SIFT-MS, there isn't really baseline noise in the same way you would have with a GCMS, and we can't really make true blanks. So really all we can do is look at the underlying noise in the system, which we know and understand, and then basically take 3 standard deviations away from that noise to work out our limits of quantitation and limits of detection over the measurement time of our methodology, which was about 25 seconds per sample. So we come up with LODs and LOQs of 4 ppb and 1.2 ppb for formaldehyde under the current method that was being run, which is significantly further away from what we expected to see in the samples we were running. So the limits of detection here are very good and well away from what we need to be worried about. So again, a good result for LOD, LOQ. So at that point, we'd covered all of the necessary parts of the ICH Q2 guidelines for method validation. And so to summarize everything we did and to give a result on that method validation, what do we get? Well, we got a pass. And so by modifying the ICH guidelines somewhat, we're able to come up with a methodology to validate this SIFT-MS method using ICH as the guidelines, and generate data that could be submitted for a regulatory submission for a pharmaceutical analysis. So to summarize that, method validation of SIFT-MS for these type of gas phase measurements, so measuring difficult analytes in the gas phase directly, is entirely achievable, and it is possible to come up with validation experiments to prove this, but we have to think about what our sample types are and how we're sampling. The point to take is that the ICH Q2 guidelines were followed to make this analysis and this validation work. But bear in mind, they are guidelines written for conventional instrumentation. They're not set in stone. They guide you through the process of doing a validation. And as long as you can interpret those guidelines and adapt to the requirements of the product or the customer with due justification, it is entirely possible to validate this data. You just have to make sure you're generating meaningful data that proves the system works. And sort of the last thing to say is, as a gas phase analyzer, you've got to be wary of the atmosphere around your system, because there is gas all around us. We breathe it every day. So we just have to be careful of blanks in this situation. But nonetheless, this has generated a method that has been validated to ICH guidelines that could be used for a regulated pharmaceutical application. So as I said, this data was generated by Joe Wicks at Intertech Pharmaceutical Services in Manchester. A fantastic set of data, and yeah, really good example of what we can do with SIFT-MS if we really try. So the next thing we're going to talk about is a more complex method, sort of based a bit more around what we would class as traditional analytical chemistry. So what we're looking at here is methanolic extractions of soil for BTEX compounds. So BTEX compounds can get into, ground soils in many ways, particularly around, fuel filling stations and other sites. And it's important to measure the level of BTEX in these samples. There are many ways to do this, and one way that is often used is methanolic extraction. And this table here shows us the process for doing this. So it's quite a complex method. You need to take 2 grams of soil into a headspace vial, add 6 mils of methanol, and sonicate to facilitate the extraction of the BTEX compounds from the soil. We then need to centrifuge that vial to push the soil to the bottom of the solvent, remove an aliquot of the methanol, which now contains our BTEX compounds, and add it to 10 mils of sodium chloride in another headspace vial, incubate that to generate headspace of the BTEX compounds, and then measure the headspace. So this has all been done before on a GCMS, but we can do this on SIFT-MS as well. So it's quite a complex sample prep, but we're still able to do that. And by using the Gerstel MPS system, we can actually automate that whole part of the process. So from the sonication onwards, through centrifugation, right through to measuring the headspace on the SIFT-MS, the whole process is automated, including the centrifugation using you know, the solvent-safe centrifuges that are available now on the Gerstle MPS platform. With the new robotic system, where we are able to change tools, it's actually probably possible to add the 6 mils of methanol into the system as well, automated. So in the end, the only thing you have to do for the methodology is actually weigh 2 grams of soil into your headspace vials and to cap them up. So we're going to follow the same approach we did before with the previous validation. We're going to broadly follow the ICH guidelines to see if we can analyze and validate this method in the same way. So the first part of the ICH guidelines refers to linearity. So in this instance, we're not making linear gas standards anymore in the way we did for the formaldehyde analysis. These are actually generating aqueous standards of BTEX compounds in water and then incubating them as a headspace method, injecting into the system as a standard headspace method. So here we've got the linear plots from about 5 parts per billion to 2,000 parts per billion in solution. And you can see here that we get really good linear plots for these 998 to plus for the R squares. In this instance, our xylene and ethylbenzene has to be measured at the same time, because from a SIFT-MS perspective, they don't look any different. So we have to do that as a combined analysis. Other methods actually are able to separate ethylbenzene and xylene, but in this instance we can't, because we need to use NO+ as our reagent ion, because we've got methanol in the background of our system. So you can see linear from across the range we hope to see in the samples. And again, analogous to what we saw before, these are the recoveries from the straight lines we saw. And you can see actually that down at the low end concentrations, down around about 5 parts per billion, we start to see poorer recoveries. Again, I think this is down to a slight skewing of the straight line, giving a non-zero intercept at the bottom end. But it does show that we're definitely able to see analysis in those solutions down at 20 parts per billion, where the recoveries are 80% plus. Next part of the validation, again, looking at system precision, so how precise are the measurements we make on this. So again, generating different concentrations of standards, this time in solution. So these are 5 ppb, 20, 200 and 2000 ppb concentration solutions in aqueous, in a headspace, incubated and measured by SIFT-MS, and we're doing repeat measurements, 5 repeat measurements for each of those samples. And you can see that we get very good precision for this system, you know, less than 10% for all analyses, apart from the very low level ones for toluene and benzene. But still, down at 5 ppb in solution, we would accept that sort of precision, RSD precision for these analyses. So again, the system is inherently precise, even for more complex analyses such as headspace generation and injection into the system. Now, as you recall from that first schematic of how the method works, once we've extracted the BTEX from the methanol from the soil, we take an aliquot of that methanol out and spike it into water, and then generate a headspace and measure the BTEX headspace after that. The method, standard method, asks for 250 microliters of methanol to be added to the system. Of course, if we're looking for more sensitivity in our system, could we add more methanol into the water? Because obviously if we add more methanol, we're actually adding more BTEX into our aqueous, and then we're able to then generate a more sensitive method. So this plot here is essentially looking at the concentration of BTEX compounds that would be seen in the headspace if we varied the methanol aliquot into the water from 50, or from actually 25 microliters up to 500 microliters. And you can see with R squares of 999 plus, absolutely we are able to do that, and the system is actually very linear over quite a broad range of added aliquot into the water. So if we needed to get more increased sensitivity, we could actually add more methanol at that point in the system. But we're going to sit with 250 microliters because it's a good middle ground concentration to add. So now we move on to accuracy and recovery. Now, because we're making these samples in aqueous solution now, we are able to do standard accuracy and recovery, where we spike in the known concentration into the sample, and then we recover back from it and look at the results. Here is an example of SIFT-MS headspace plots for accuracy recovery samples at 17, 42, 83, 166 and 333 parts per billion in the solution. So we can see that the data generated by the system. And you can see here that when we run the spike concentration across that and recover it back out again, we still see the linearity that we expect to see on that system. Again, R squares of 998 plus for that system. And just to show that what we spike in, we expect to get out, if we plot the spike concentration versus the calculated concentration from our linearity curve, we would expect to see a very good regression line, which we do at 997. We would also expect to see a slope somewhere close to 1, which shows that there is a one-to-one relationship between what we're spiking into the system and what we get coming out from the calculation. And you can see from the plot here that our slope is 0.98, which is as close to 1 as you could probably ask for a method of this type. So again, the accuracy and recovery, what we put into this system, we get back out again, absolutely. And also just to show that the recovery is good across the entire concentration range. These are our percentage recoveries from that analysis. So somewhere between 80 and 110% recovery for each of those concentration spikes. The next one is analytical precision. So making up 200 ppb solutions of analytes in the water and generating headspace and injecting into the system, and then running repeat analyses and seeing what R squares we get. And you can see here that for each of these analytes, we get R square of 1% or less. Again, I will hasten to add here, there is no internal standard in this method. So this is all analyzed as it comes out of the headspace. There's no normalization with an internal standard. So again, analytically, the system is inherently precise. And just to show that the recoveries from this is very good, so when we back calculated these concentrations, we recovered close to 100% of what we expected to see for these analytical recoveries. And with that, I'd like to finish the presentation and say that we can validate both gas phase and more traditional and complex analyses using SIFT-MS and following those ICH guidelines is entirely possible, but what we need to do is consider the methodology, consider the approach that we take to generating the samples that we're going to run through the system to generate meaningful data that can be used to prove that these systems are valid. So absolutely, the question, can you validate SIFT-MS methods? Absolutely you can. So with that, I'd like to hand over to Vaughan to take any questions. Thank you.
Brilliant. Thank you very, very much for that, Mark. That's excellent. We do have some questions. The first one is, how long did these validations take? And are there situations where you would think that they could be shorter or longer than what you've experienced here?
They didn't actually take very long. My experience of doing sort of chromatography validations, they can take anywhere between 4 and 6 weeks to do, whereas for the methanolic extraction one, that whole set of data was gathered within 5 days of lab time, simply because the methodology is so much quicker. We get results so much more quickly. Again, with those formaldehyde validation, to generate that linear plot, which had, I think, about 14 data points on it, that was about 1 hour's worth of work to generate 14 data points for a linear plot. So validations aren't very long when compared to the traditional approach to doing validation work. Could they be shorter? I think if you were in a desperate hurry, you could probably shorten them down a bit, particularly for the second set of data, which being highly automated from beginning to end, you could definitely set that method up to run all through the night and generate much more data than doing it during the day, which we did. Would they be longer? Depends what you're looking to do. It all comes back to, I suppose, what is the data you're looking to generate? So it's generating meaningful data. So there may be situations where you might be looking at running standards that have some stability attached to them. So you're generating standards for your linearity plot, or for your inherent calibration approach to your system, that you may not want to prep up every time you run the system. You may want to run stability data, in which case your method validation is going to take as long as you're prepared to hold your samples for the stability, I suppose. It's an interesting question. Do you want them longer? I mean, there are situations where they will be longer, but yeah,
Yep.
definitely shorter than GCMS.
Yeah, excellent. Do you have any thoughts on how to validate analysis that involves a more traditional SIFT-MS usage, that is, for example, continuous analysis rather than automated analysis?
Yeah, I think the first validation exercise with the formaldehyde is closer to what would be classed as traditional SIFT-MS, because in that method, you're basically analysing direct gas phase stuff in bag. So that's much closer to what would traditionally be done with the SIFT-MS method, I suppose, where you're looking just to analyse the the gas phase around you. As you say, the second version is much more of a automated analytical method. So yeah, I think you could. Again, you've got to consider what you're trying to measure. Of course, if you go back to those ICH guidelines, which are really useful when you're looking to validate a method, they do have some things that I think have some use, some principles that are used across all analytical methods, regardless of how you're doing it, such as, is your system linear? Even if you're doing continuous monitoring, what you want to be sure is if your continuous monitoring leads to sort of spikes in concentrations from, say, 0.1 to 100 ppmv, you want to be sure that your system is linear across that entire range, so that when you see these changes in concentration, that your system is right. And so a linear analysis would be very useful. Precision, again, prove your system is precise. If you measure today, measure in a week's time, you're going to get the same result. Do your precision, do your intermediate precision on it. So those ICH guidelines do actually point you to some very useful data generation to look at more traditional SIFT-MS methods, I think. I think it'd be useful to validate SIFT-MS methods in this way more often, if you want my opinion.
Yes, I think so. The short answer there really is yes, isn't it? I guess.
Yes, exactly.
Yeah.
Why use one word when you use 1,000?
Yeah, that's right. Yeah, I agree. You said that you didn't use internal standards in that second example. Are there situations where you think they could be of benefit to SIFT-MS measurements, and would traditional isotopically labelled standards work with this technique, do you think?
Yes. Now, there were two reasons why internal standards weren't used in that method. The first one is that my experience of doing particularly automated SIFT-MS measurements is that it doesn't need an internal standard. It seems to basically be very precise without that. And I think that's because the marrying up of the SIFT-MS method with the sort of headspace type analyses we do works really well. And so I think we get really nice injections into the system. So we don't really need to use an internal standard. I suppose one thing you could use an internal standard for is not so much to use it to normalize variability in your instrumental methods, which in some instances is what internal standards are used for, but actually to follow changes in your sample prep. So it's acting not so much as an internal standard as something that's checking that your sample prep. It's more like an injection standard, I suppose. So if you've got a complex prep like that methanolic extraction prep, you want to be sure that all stages of your preparation, you're not losing analytes in unusual ways that you're not aware of, so that your recovery from front to back is good. So I could see in that instance, put in an internal standard or some form of injection or method sort of tracking standard would be a useful exercise. Of course, what do you pick? Because traditionally, as you say, isotopically labeled standards are the way to go. So for example, for the BTEX analysis, you might want to use toluene D8, so deuterated toluene. Problem with SIFT-MS is that we have no separation on the system, and so by adding 8 mass units onto toluene might actually make that toluene D8 look like something else. For example, MIBK. it wouldn't look like deuterated toluene anymore. It looked like a completely different analyte because the molecular weight has changed. So actually, finding useful internal standards is more difficult than you might imagine. And what you really need to do is find an internal standard that behaves like your analyte, but is a significant number of Daltons away in mass from your analytes of choice. So maybe perfluorinated compounds as opposed to deuterated compounds might be an approach here. It's definitely worth looking at, but it's not as straightforward as you might imagine at first look, I would say.
Yes. What about, there's a question here about specificity. Will increasing the number of compounds in the method potentially lead to specificity issues? And if so, what sort of revalidation would you, well, I guess so, or if not, what revalidation would you need to use if you added more compounds?
Yeah, I mean, if you add more compounds to your method, then of course, in any method, not just SIFT-MS, in any chromatography method, the more things you're looking for, the more chances you've got of something unknown hitting one of your analytes. And so in all cases, adding more compounds increases the problems with specificity. And for SIFT-MS, you know, again, this is potentially an issue because we don't have separation in time. So we're separating using reaction chemistry and mass. And so some analytes can look exactly the same and be entirely different. And so in that case, I don't think you could get away with just looking at the library and saying, I don't see an analyte that looks like my analyte at that mass. I think what you would need to do is probably make your method look at the analytes of choice using more than one reagent ion. I think that would be what you would need to do, use the multiple reagent ions of SIFT-MS to act as almost a qualifier to your analysis. So your analyte is being qualified by multiple measurements, which would mean that if anything sat in the system you weren't expecting to see, it would add to a signal and it would then show up in that sort of qualifier type way, which would mean you would have to revalidate the method to look at multiple reagent product ion pairs, I suppose. The other thing you could do, of course, is to spike in what you might think will be potential issues with your method and see if it does actually lead to real issues when you get the analysis done. So that actually is beginning to look a bit like a combination between specificity and recovery, I suppose.
Yes.
Interesting.
Yes.
But yeah, more compounds is more specificity issue.
Yeah. Yeah. Now, here's a question for the automation guru. How do you envisage setting up SIFT-MS sequences once you've validated your method? So here they mean, well, to elaborate a little bit, looking at SIFT-MS being set up with that validated method for routine analysis.
Mm-hmm. Well, what I would do is, being a very, very long-serving analytical chemist, is I would make sure that my method, having validated it, of course, has enough checks and balances in it to ensure that when you generate data, it's producing the right data every single time. And pretty much what I mean by that is you need to run calibrations with your methods. So the standard way of doing it would be you run a calibration curve, maybe 5 or 6 points at the beginning of your analysis. Then you run some samples, and then you run some form of QC check through the middle of that. So maybe a standard and known concentration. Run some more samples, another QC check through the method. Because one thing to say about SIFT-MS methods, and particularly automated SIFT-MS methods, we can get through an awful lot of samples in one go. We can get through hundreds of samples a day, which is normally outside the scope of a GC or LC method. And so you really want to be confident that your system isn't drifting around across all that sample. So I would batch it up with calibration set at the beginning, take you 10 minutes to run, set of samples, and then a quick 1 minute QC check every so often. And just look and see how that QC is running. It acts as a very, very good check through the system, and it allows you to sort of check for historical problems in your method. That would be how I would do it. Yeah, stick QCs in there every so often. It doesn't cost you much to do. Automated anyway. Probably don't even have to prep them.
Excellent. So, what do you think? A bit of a pharmaceutical question here. What would SIFT-MS be useful for rapid screening of packaging materials or ingredients, such as application in a quality by design approach, or QBD.
Yeah, absolutely. In fact, by doing these sort of screening methods, actually they make the validation a lot easier, because what we're trying to do with the validation is come up with a method that will give you an answer, and in many cases those methods are looking to give you an absolute answer. So what is the concentration in my product? For these type of screening methods, all you're really doing is you're wanting to look at a pass-fail. So you're saying, is my sample below or above a specification limit? And in those cases, it's a much easier exercise to validate, because all you really do is you look at the system at the specification limit, and that means that your validation exercise is a lot easier. It also means your methods is a lot quicker, because all you're really doing is running a sample really quickly. Does it breach my spec limit or not? And if it does, throw a red flag up. And that means that by, as you say, this quality by design approach is that you're screening materials before it even gets into the production stage to produce a product that may end up inside a pouch, that may form formaldehyde, that may need to be analyzed for formaldehyde. So if you had taken those polymeric materials and screened them up front, you would have had a much easier exercise at the back end of that method, I think. Yeah, these screening methods are really easy to put together. Yes. They're the best ones to do.
Okay.
Pass or fail.
Yep. What about another question related to polymers a bit? Is there a way that you can measure absolute quantities of volatiles in materials? And if so, how would you validate it?
I'm assuming, if this is associated with that one, that we're talking about volatiles in solids, so VOCs coming off of polymers, for example. So we've covered this in some previous webinars, actually. So the best approach for this is to actually do an MHE, so a multiple headspace extraction type method, where you actually extract the sample multiple times and fit it to an MHE plot, and then that calculates, using extrapolation, total concentration in the sample. Again, the validation exercise is similar to any other method. I have validated one of these for a GC method before. Again, what you do is you look for things like linearity, you look for things like precision of your instrument, you look for things like recovery into your sample. Slightly harder to do because you've got a solid material, so how do you put material into that sample? Maybe use the approach that was used for the formaldehyde validation. Use a low and high end sample, or small amount of sample versus high amount of sample, and see if these are still linear across the range. So the underlying system parts of it, linearity, LOQs, precision, all exactly the same. Then all you've got to do is run your samples as you would run them and show that what you expect to see, you see. So the bulk of the underlying validation is the same. I think what we want to get from this webinar is, underlying everything is that a same set of things you want to do for a validation exercise. Validate your instrumentation as much as your method, and it's easy to do. Linearity, precision, LODs, intermediate precision. It's really straightforward.
Excellent. There's also a question here about whether you can use toluene. I think this must refer to soil as toluene to extract volatiles. Is that a possibility with SIFT-MS?
No, short answer.
I'd agree.
Well, yeah, the short answer is no, because too much VOC.
Yeah.
Ooh, could we do it by some other approach? I don't see it. Toluene just is such a nice VOC for SIFT-MS that, you know, you can see it at parts per trillion with SIFT-MS. Yes. You could never get, you know, it wouldn't work.
Yeah,
sorry.
Yeah. We do. There's the point that we do need to make, that we are a bit limited. We don't have chromatography to, as Mark's implied in his answer, to separate out the solvent. So if it reacts with the majority, or all, well, if it reacts with all of our reagent types like toluene does, then we can't really use that as a solvent. It will just overwhelm the instrument signal.
It's like basically swamping the mass spec in it, basically.
Yeah, exactly. There's no column to protect the instrument from the solvent. I think one last question before we wrap up today. Could the high throughput provided by the SIFT-MS instrument be used to speed up method validation for conventional analytical techniques or methods?
Yeah, that's an interesting question. I think it could. I mean, you know, I'm very much a strong advocate for SIFT-MS, but I'm definitely not, you know, I do all sorts of analytical techniques, and it depends on the method, of course. Let's say we're looking at headspace, for example. One of the things you want to do is maximize your headspace concentrations or understand your equilibrium concentrations in the headspace. Now, we can do headspace measurements so much faster than you can do with GCMS. So actually, you could set up a method to vary, say, incubation times or temperatures in an automated system and get the answers out from SIFT-MS to show you, broadly speaking, the analytical space you're in, and then using that data for the incubation time and temperature, use that back in another method such as GCMS, and then do your separation. And so there is a complementarity here. I think you could definitely do it. It would aid with your method development times, absolutely.
Excellent. Well, thank you very much, Mark. I think that's all we've got time for today. Very, very helpful presentation, and also very interesting questions that you've addressed very well. So thank you for that. Thank you, everybody, for listening to the webinar today. The webinar will be available from early next week on demand if you would like to listen to it again or share it with colleagues, and an email will come out to you with the details of how to access that recording. And I guess in a few days as well, it will be available on SIFT's website. So thank you again, Mark, for your fine presentation, and thank you everybody for attending.
Thank you.